Have you ever flipped a light switch and just wondered what really happens in that instant? I mean, it feels like magic, right? Well, today, we're going to pull back the curtain. We're going to follow the incredible journey of electricity, all the way from a massive power plant to the battery in a car, and we're going to do it at the atomic level. Let's jump in.
Okay, so to really get our heads around this, I want you to imagine a huge costume party. Now, here's the weird thing about this party. There's only one guest, and its name is Energy. And this guest has a golden rule. It can never be created, and it can never be destroyed. All it does is change costumes over and over and over again.
And on our little adventure today, we're going to see Energy wear three main costumes. It's going to start out as the kinetic energy of moving water, then poof, it'll transform into the electrical energy of a push wave, and finally, it'll get stored as the chemical energy of a stretched spring. So let's see how it pulls off that first amazing quick change.
Right, our story kicks off at a gigantic dam. This is where it all begins. This is where the electricity that powers pretty much everything in our lives gets its very first powerful shove. We're going right inside the generator to see exactly how that push is born. But before anything happens, let's zoom in. I mean, way, way in on a simple copper wire. You might think it's empty, but it's not. It's packed with what physicists call an electron sea. Just imagine billions and billions of tiny electrons just drifting around, lazily, in totally random directions. There's no flow, no purpose, just a calm, disorganized sea of particles. So how in the world do we get them all moving together? Well, with a magnet. But look at this comparison here, it's so important. If you just lay a magnet next to the wire, nothing. The electron sea just stays calm. The secret ingredient, the absolute key, is change. When a generator spins that magnet, its constantly changing magnetic field is what whips up that sea and creates this huge coordinated wave. And that collective push has a name we all know: voltage. Now, this is the really crucial part. Voltage doesn't create any new electrons. It's not a source of particles. It's just the pressure that gets all those billions of electrons that are already in the wire to finally get organized and move in the same direction. You know, think of a water pump. It doesn't make water, right? It just pushes the water that's already sitting in the hose. Same idea. Okay, so we've created a push, a voltage. Now, that push has to travel, sometimes hundreds of miles to get to our homes. And this is where we get into one of the biggest and honestly most mind-bending mysteries about how electricity works. So here it is, the big question. When you turn on a light, is that because a single, specific electron that started its journey at the power plant just finished an epic marathon and finally slammed into your light bulb? What do you think? The answer is a huge, resounding no. Not even a little bit. The reality is actually much, much weirder, and if you ask me, way cooler. It's best explained by what's called the billiard ball effect. Just picture a super long tube packed from end to end with billiard balls. They stretch all the way from the power plant to your house, and these are our electrons. Now, the generator, that's the voltage, gives a sharp push to the very first ball. And what happens? Instantly, the very last ball at your end of the tube moves. See? The first ball barely budged, but the push wave, the energy, traveled the whole distance in a flash. And this just perfectly shows us that electricity has two totally different speeds. The energy wave, that's the message to get moving, travels at nearly the speed of light. That's why your light turns on the second you flip the switch. But the electrons themselves, the little messengers, oh, they are unbelievably lazy. They just kind of nudge their neighbor and drift along at the speed of a snail. Literally, the first electron from the power plant might not even reach your house for a few years. Okay, so our super fast energy wave has finally arrived. It zips through a charging cable and right into the battery of an electric car. And this brings us to the final act of our journey, and you guessed it, another huge misconception. We all say it, right? I need to fill up my battery. So does that mean a battery is kind of like an empty bucket and charging it is just pouring electrons into it until it's full to the brim? And again, the answer is a simple, clean no. Get this, a full battery and an empty battery have the exact same number of electrons inside them. They don't store electrons at all. They store something completely different. What batteries actually store is potential chemical energy. So charging a battery isn't like filling a bucket, it's more like stretching a rubber band all the way back, or pulling a really heavy weight up to the top of a hill. You're using energy to force something into a tense, unstable, high-energy state that's just waiting to be released.
This water slide analogy just makes it all click. Think of the lithium ions inside the battery as a bunch of kids at a water park. When you're charging the battery, you're using that electrical push to force all the kids up the ladder to one side, which is called the anode. A full battery is just all the kids piled up at the top of the slide, buzzing with potential energy. Then when you use the battery to drive your car, you're just letting all those kids slide down to the other side, the cathode, and they release all that energy on the way down.
And just like that, our guest, Energy, has completed its incredible journey and gone through a whole series of amazing costume changes. Let's just quickly recap the entire cycle from start to finish.
So, we started with the kinetic energy of moving water. That was transformed into electrical energy, that super-fast push wave. That push then traveled through the wires and was used to create stored chemical energy in a battery by pushing those ions uphill. And finally, when you hit the accelerator, that chemical energy is released, transforming right back into the kinetic energy that spins the car's wheels. So you see, we've come completely full circle. No energy was ever lost, and none of it was magically created from nothing. It was all there from the very beginning, just hanging out at that cosmic costume party, waiting for its next amazing transformation. And that really brings us to a final thought. This journey is a constant, never-ending circle of change. The kinetic energy that moves your car becomes heat energy from friction in the tires and brakes. So the real question is, as you go about your day-to-day, where else can you spot energy getting ready to change its costume? Once you start looking, you see it everywhere.